That is easy, I think.
Okay. Thank you. So if anyone has any doubt or anything, so please ask. Otherwise, I will solve the second one. So okay, so if anyone has any doubt, so please ask. For second question, it is simple one, linearly dependent independence. You know how to prove this. If V1, V2 and Vn are vectors, if you want to show that these are linearly independent, so how you will show this one? Just take C1 V1 up to Cn Vn equal to 0 and solve it. That implies each Ci equal to 0, I equal to 1 to n. So if you get this one by taking this linear combination, then we say the vectors V1, V2, Vn are linearly independent. So using that, you can easily prove that this one is linearly independent and find the condition for linearly dependence. And this one, if Vn has a basis of n elements, give a detailed proof that V is isomorphic to
Sir,
Fn.
can you tell how to find the condition to make it linearly dependent?
Okay, let's try.
I think if we take the field as Z3, then it will work, I think. Then the
Yeah,
last vector will become 0 vector, and then we can.
I was thinking the same. Like this is
yes,
becoming the only possibility to make it really independent, right?
yes, you have to take some finite field concept. Then yeah, that's easy. No, it becomes 0, so it becomes dependent. Okay, and okay, how you to solve question number 3? Anyone?
Since the basis has n element, then we can present any vector of V as so alpha 1 V1 plus dot dot alpha n Vn. And then if I take the map as V goes to alpha 1, comma alpha 2, comma alpha n, then we can show that that will be a homomorphism and also 1 and 1 2 mapping.
Yeah, correct. So you just, if basis has n element, this means it has dimension n. And again, as yesterday I have told that if two vector spaces have same dimension, then they are isomorphic, and you can use that proof. And actually, it is asking about that proof, that if two vector spaces have same dimension, they are isomorphic. So if I just take basis element of this and this, so map basis element of here to here, one to one in one-to-one correspondence. And if the basis element map one-to-one correspondence, then they define linear transform or homomorphism, and they become isomorphic to specific. Okay. What about question number 4? If T is isomorphic of V onto W, prove that T maps a basis V onto a basis W. Okay. So it's saying that T from V to W is isomorphism. So you have to show that it maps basis to basis. Okay. So anyone, how to solve this or how to approach this problem? Has anyone has tried this question?
So it's basically if we have a basis of V, like V1, V2, Vn, then the claim is that the TV1, TV2, TVn will be a basis for W.
Yes, yes. Okay. So how you have to show two things. One, these are linearly independent, and the second one is this spans the W. Is it correct now? So how
Yes,
you
sir.
will show that this is linearly independent?
Start with alpha 1 TV1 plus alpha 2 TV2 etc.
So we consider a linear combination.
Yes, okay. So let's say alpha 1 TV1 up to alpha n TVn. After that,
So this is equal to 0 we'll consider, and then using the properties of linear transformation, this will be T of alpha 1 V1 plus T of alpha plus alpha 2 V2 up to alpha n Vn. Yeah,
okay.
equals to
Okay. After that,
Because this is a linear transformation, so alpha 1 v1 up to alpha n vn should be equal to 0. The sum
Why,
should
why,
be
why it is 0?
p map 0 to 0.
Yeah, but it can map other 0 other than 0, na? Means we can map, na? T of V1 is also equal to 0 or not?
But this is this is an isomorphism, so
Yeah. That's I want to listen. Okay. So you have to use the isomorphism property. This become alpha 1 V1 plus up to alpha n Vn equal to 0 since T is 1. So that's what after that you will get alpha is at 0. Okay, and okay, what's the problem? Hello, I'm audible?
yes, sir.
Okay.
Yes, sir.
Okay, thank you. So, okay, this part has been done that it is linearly independent. So, how we will prove that it is spanning that set W subspace? Yeah, vector space, sorry. Anyone? How will you, so that if you take any.
So these vector will form a n-dimensional service.
We'll use the fact that T is on to.
And
Please anyone, please one by
W
one.
has
Okay, yes. Divyansu, please continue. One by one. Anuj, sorry. Anuj, please continue how to approach this problem, this solution.
We'll use the fact that T is on to. So because T is on to, so for
Yes,
any W in W,
yes.
W can be written
sir,
as
Divyansu, your voice is not clear. I think you have any network issue.
these
Divyansu, your voice is not coming clear. You have network issue, I think.
n vectors will form the n-dimensional subspace.
Yes. Okay, Anuj, please continue. You. Divyansu
so
has
W
submitted.
can be written as
Yes.
T of some V
T of some V equals to W since
when
T is
on
onto.
to.
Okay.
And again,
Now,
V1 to Vn is a basis of V, so this V can be written as a
Linear.
that's okay, na?
and yeah, using the fact that T is a
So yeah,
homomorphism. So
T alpha 1 up to that alpha n T Vn equals to W. So if we span the W also. So now the second thing is we are taking here finite dimension n, but here it is not mentioned anywhere that it is finite dimension. No, it hasn't mentioned anywhere it is finite dimension. Please note that this question. Okay, we have done it for finite dimension. We have taken n, but it has nowhere mentioned that it is a finite dimension vector space. In this question, it is only said that V map onto and T is isomorphism. So we have to prove that T map basis of V2 onto basis of W. Nowhere it is mentioned that V is a finite dimensional vector space. So now we have to change some little bit in the proof. The approach will be same, but the technique will little bit different. We can't take finite, we take infinite set, yeah, arbitrary set. No? So how to approach for means how you will do to prove that it is true for any arbitrary vector space, either it is finite or it is infinite.
So won't it move on the same grounds? Like if
Yes,
B is a basis, then even if it's infinite, the linear independency will follow from if every finite set is linearly independent, and
okay,
that we have
so
already proved.
okay, so yes, linearly independence will be proved by same technique, but you have to write 1-2 sentence to conclude your statements.
Yes,
How
sir.
it is going to be
Like
linearly
basically
independent.
the claim would be if B is a basis, then TB would be a basis for W.
Yes. So you will able to prove that TV is linearly independent. Okay, by the same technique and just taking any finite set which of B is linearly independent, so it is obviously linearly independent. Now for spanning, how will you prove that it spans T of B spans W?
Even in spanning, when we take the linear combination, it is a finite linear combination of elements of a basis.
Yes.
So for those elements, we can take the image and it will be the free image in using the onto thing that we have done already.
Yes. Okay, correct. So yes, everyone understand this point. If you done for finite only, it will not prove solve this question whole. You have to prove for arbitrary vector space V and W. So you have to use this way to conclude your logic and approach. Because if it's not given here, it is a finite dimension or infinite dimension. So you have to take any arbitrary vector space and solve for that and show the results for that. Okay. So anyone has any doubt in question number 4? If anyone, please ask. Okay, so our question number 5. If V is a finite dimension and T is isomorphism V into V, then prove that T must be onto. Okay, it's saying that T V to V 1-1 isomorphism. Isomorphism essentially it is saying 1-1 homomorphism. It's the language of this book is a little bit different. Then it's saying that so that T must be onto. Okay. So how to solve this one? Anyone? If T is a map from vector space V into V itself and T is 1-1, then we have to show that T is onto.
We can prove that if V1, V2, Vn is a basis,
It is okay.
then TV1, TV2, and TVn is again a basis. That is, it is
Yes.
n-dimensional. So TV1, TV2, TVn are alike. That we have proved.
Yes, we just by spanning, or we can say that. Okay, no. Okay,
Yes.
so T will it will become basis. Okay, after that.
Now it will. It forms an n-dimensional subspace inside inside the V, and V has also the n-dimensional. So we can conclude that TV1, the span of TV1, TV2, and TVn equal to V.
Okay, yes. Okay, approach is correct, but you have to write little bit more for mathematical to prove that okay, onto that is let an element of V belongs to V, and then it has a pre-image. The approach is correct. Your approach is just using that, but you have to find a specific element for each. If you take any V belongs to V,
Yes,
then V can be written as some a linear combination of that after that, so you can prove that. Okay.
Can we say in a defined way like domain and codomain both have same element? So if the T is not onto, then there will be one element in codomain which does not have any preimage. So basically, two element of domain will goes to at least two element of domain will goes to some one element in codomain, and that will contradict that T is 1-1.
Yeah, it is same, but you approach the same, but you have to use the isomorphism and 1-1 ontuness.
Okay.
It depends on the approach is correct, but you have to use mathematical tools. You have to given T is 1-1 and this T is isomorphism. So you have to use these two facts, and you can approach by that. This implies otherwise contrapositive that if it is not 1 onto, then it will not be in 1-1. So it's okay. Not P implies not Q, or you can use P implies Q. Straightforward way. Okay, and the second question in this part that is had been given. It is you have proved that this one is for finite dimension. Okay, question number 5. It has given finite dimension. What if we put V to be infinite dimension? Infinite dimensional, if we say, then this result will true or not? If we map have T V to V a 1-1 map, and this implies T is onto or not? Yes, anyone? If we saying that V is an infinite dimensional vector space and T is a V to V map, which is 1, 1, does it imply T is onto? Anyone, any approach, any comment?
So we can take the set of all vector space of all polynomial functions over some real numbers.
Okay, set
Px
of all polynomials. Okay.
over real. So this is a
Okay.
vector space for R.
Okay.
And it has a basis of the form 1x, x square, and x to the power n like that.
Okay. Basis has element 1x up to x power n and so on. Okay.
So I am mapping 1 to x, x to x square, like I am leaving 1 and mapping
X
1
to
to x,
and
and to
x
x
power n plus 1.
So this is 1 mapping, but not onto map, because 1 has no pre-means.
Okay, yes, correct. So everyone got the point or the solution? If you map taking the basis this one and map every that if you approach this, if you take any polynomial, it will be form of a0 plus a1x plus up to an x power n for some n. So it's saying that if we map T of px equals to a0x plus a1x square up to an x power n plus 1. So if you can visualize a little bit, if you divide by 2, divide by n plus 1, then you will get that it is an integral transformation. If of px equals to 0 to x pt dt. So this is a linear transformation on this, which is 1, 1. You can easily prove, but not onto. Okay. So this is an example. You have to verify yourself that it is 1, 1, but not onto. But it is a good question to think about. What about infinite dimension? So yeah, many times it happens that results which are true in finite dimension may not be true in infinite, and similarly hold for infinite also. Sometimes it's some results true for infinite but not true for finite. Okay. So now what about question number 6? Again, V is a finite dimensional vector space. T is an homomorphism. V onto V. So the T must be 1, 1. So an isomorphism. Again, you can prove that one will be similar to this one. Just given that T is onto, then T is 1, 1. So okay, you will try. Okay, similar way you can try. Question number 7. If V is of dimension n, so that any set of n linearly independent set in V forms basis. Okay, this one is easy question, but I want to listen how you will write this question. Okay, anyone? It's saying that yes.
Yeah, so we can, if that is not a that is not a basis, then we can extend that to a basis. And if that contains at least one more element, then it will contradict that the dimension is n.
Okay, got it. Repeat once more. You are saying that you are taking.
Yes, if the n linearly independent vectors not forms a basis, then we can extend that to a basis of V. And if that contains, we can extend that to a basis that would contain those n linearly independent vectors. And
Yes, got it.
if our basis is at least contain at least one more element, then that would contradict that dimension is n.
Yes, got it. So what he's saying is that if we suppose, always going to in contradiction way, suppose if, okay, let's say S is a set, say V1 up to Vn are linearly independent. If S is not basis, then by extension theorem we can extend S into a basis for V, and this implies, if we extend, this implies the cardinality of S must be greater than n, and this implies dimension of V become greater than n, and which is a contradiction, because it given that V is of dimension n. Okay, so if okay, so anyone has any doubt how to write this or how to approach this problem? These are some easy problem, but sometimes it becomes difficult to write how to write this. So that's why we are doing this. Okay, question number 8. If V is a finite dimensional vector space and W is a subspace of V, such that dimension of V equal to dimension of W, then prove that V equal to W. Okay, how to solve this one? Yes, anyone? Rumik goes.
So W has a basic element which is equal to dimension of V.
Yes. Dimension is equal again. What you say?
So we can use the previous result from the question number 7.
Yeah, just
Because
how to
W
write?
will
How will you
have
write? Just give complete.
W as a basis of n element
W has
and the elements in V.
and V has also, okay, let's say basis of W and basis of V equal to which is V to Vn. Okay.
And these n elements are linearly independent from because in W these n elements are linearly independent.
Yes, yes.
And they are in V. So
okay.
they will also form basis for V, because from question number 7 we have seen that n linearly independent vectors form a basis.
Yes, yes. So it will follow from question number 7, and you have to write little bit just in the last to conclude your statements. You have to change the language only.
We cannot use the question number 7 in the exam or like that. We have to write full.
Yeah. So for exam purpose, you have to then state or prove the question number 7 statement prove, and then use directly, and then write 2-3 line and then conclude your answer.
We can write the question number 7 prove, and then we can do it.
Okay, for question number 9, again V is a finite dimension and T is homomorphism of V into itself, which is not onto. This implies T is a map from V to V, not onto, and it is finite dimensional vector space. Then we have to show that V not equal to 0 there exists such that T of V equal to 0. It is the notation is of written as this V of T equal to 0. We are using this notation. So okay, how will you prove this one? Yes, anyone?
If this not hold, then it will contradict that this is onto. This is not onto. Actually, we have done that. If basically if T of V not equal to, if T of V not equal to 0, then T will be 1 and V is finite dimensional. Then T will be again onto. We have done that earlier, so that will contradict that T is not onto.
Yes, yes, correct. So these all questions are related to each other, and you have to, if you are especially for writing answer for each specific question, so you have to know how to use the previous result and how to write this one. These are related to each other, but a little bit tricky one to write to conclude your statements in getting the right answer. Your solution is correct. If it is not possible, if for T of V is not equal to 0 for all V not equal to 0, then you can conclude that this T become onto, and if this implies contradiction because it is given that it is onto. So this implies for some V not equal to 0, T of V must be 0. That's he is saying. Okay. So now for question number 10, F be a finite field, Fx is a polynomial in X over F, prove that Fx is not finite dimensional vector space. It is easy. You can take that 1x, x square up to x power n, and so on. And so how will you show? Okay, this is easy one, but you have to show that these are the elements in belongs to f of x, and this one is infinite set. Just you have to show this set is linearly independent. You can take any, this one is the easy one set, we have seen the simplest one. But to show that any set which is not finite dimensional vector space, so you have to show that there exists at least an infinite set which is linearly independent. Because the definition of basis is one is that it is the largest linearly independent set, and the cardinality of that set is defined as dimension of that vector space. So we are showing here that there is a set which is infinite and this is linearly independent. So this implies the dimension cannot be finite for this. Now question number 11. This P of x its dimension is less than n. T. This is the map defined like this. What they have done? Okay, just replace x by x plus 1 and prove that T is an isomorphism of V onto self. So yes, it is an easy one. You can just use 1 1 onto, and so that it is linear transformation. And those who are doing first time linear algebra course, for them you prove that this one is form a vector space, means it is a vector space over F. You have to prove this also. Those who are doing first time linear algebra course, for them. Okay, for question number 12, let W equal to this one. This one is the condition it is given here. So that W is a subspace of Vn and find the basis of W. Okay, so how will you find the basis? Okay, subspace part is, I think, easy. So how one should find the basis for W? Okay, anyone? Anyone? How should you approach to find the basis for this one? Yes.
Alpha n minus 1 can be written as
Yes.
minus alpha naught minus alpha 1 minus alpha n minus 2.
Okay.
Minus alpha 1 minus alpha n minus 2. So we will have a basis of the form alpha, say 1x x square x to the power n minus 2 and minus.
Just please stop for 2 seconds. Okay, just wait. Hello. Yes, Divyansh,
Yes,
please
sir.
continue. Divyanshu?
Yes, sir. Okay.
Yeah.
I'm just thinking.
Okay, okay.
Just 1 minute. Yes, sir.
Anyone else? Any approach for this one? How to solve or approach?
So replace any of the scalars like alpha naught by minus alpha 1 minus this, then take the alpha is common, then the basis will be x minus 1, x square minus 1, x to power n minus 1.
Okay, just say again. I will write it so you will see. You said just take alpha 0 and what does it means? Okay, let's visualize how the sum of the coefficients of that polynomial. All this is a polynomial. Means if you take any polynomial, the sum of the coefficient must be 0. That's it is saying in language form. So it means this, if you take alpha 0 to be fixed, just one by one fixed, okay, means if you can choose okay, alpha 1 plus alpha 2 plus up to alpha n minus 2 equal to minus alpha n minus 1. If we take this one, this will satisfy, no problem. If we take any polynomial with this coefficients which satisfies this condition, this is equivalent condition to this. We have not written anything else, but just the similar condition, and then impose this on this one. What does it mean? How will you write? You can write this polynomial. Okay, let me see some space. So you will write alpha 0 plus alpha 1x plus up to alpha n minus 2 x power n minus 2. Okay, minus alpha n minus 1. No, okay, sorry. Just 1 second. Okay, a little bit tricky one. Alpha 0 plus alpha 1 dot 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 alpha n minus 2 x power n. This will form an element of this. Now means okay. So how will you choose the basis? This one is the condition we get that okay. If you can see that we can choose in out of n minus 1, 0 to n minus 1, 0 to n minus 2 elements without any restriction. You can choose any without any restriction. So this shows the dimension of this one is this has dimension n, so it will have dimension n minus 1. First of thing means we have only one restriction, that is if we fix 0 to n minus 2 element, then n minus 1th coefficient of this expression will be dependent on others. So we can remove from there. So we can conclude from there that is the dimension of this space will become n minus 1. Now to get basis exactly, so okay, how we can get this one? Okay, we know one basis is x square up to x power n is a basis for okay, basis for this one without any condition. Now we are putting some condition on this. Okay, we can find one basis directly, but it is not sufficient, I think.
So we can look at the basis of the form alpha naught comma alpha 1x up to alpha n minus 2 x n minus 2, and in place of alpha n minus 1 we will put what we have got for the alpha n minus 1 into x n minus 1. This will be a basis, and dimension will be n because we have the restriction on scalars, not on the x.
Okay, again once again what you are saying, dimension?
So dimension will be n because we have the restriction only on the scalars, not on the x square.
No, the dimension will be n minus 1. Since we have a one condition on it, it will reduce one of the scalars. We have one less restriction.
And with this condition that I realize that you can choose n alpha 0 alpha up to alpha n minus 1 to alpha minus 2. You can choose any number. Then so you will have condition on this one.
How x to the power n minus 1 will be written as a linear combination of the
I am not writing linear combination of this. I am writing the coefficient only in linear combination, not the whole term. That is given here, not I am writing anything extra, just this term. This is the coefficient which are written in linear combination. Just I am writing this one is at minus alpha 0 plus alpha 1 up to alpha n minus 2. This only. So if we choose any alpha 0, alpha 1, this one, then we can write alpha n minus 1. This is the coefficient, linear combination coefficient of this, and this one is linear dependent. Means this is the restriction that is we have to apply.
Okay, so we are looking it as a subspace of Fn, not as
yes. So for basis, we can choose. what we can choose as a basis means
So
this
for
some
basis,
X.
replace alpha naught by minus alpha 1 minus alpha 2 minus alpha n minus 1. Then take alpha 1 common. It will be alpha 1 x minus 1 plus alpha 2 x square minus 1 up to alpha n minus 1 bracket x n minus 1 minus 1. So the x minus 1 x square minus 1 up to x n minus 1 minus 1 will be the basis for this W.
Okay, so that tell me again what is the basis finally you get from here?
X minus 1
X minus 1
comma x square minus 1
x square minus 1
up to x n minus 1 minus 1.
minus 1.
This comes after we replace alpha naught by minus alpha 1 up to minus alpha n minus 1.
Yes, yes, got it, got it. Means you have to use this one and just this one is constant. You can use this one now up to alpha n minus 1. Is it correct that you are saying?
Yes, sir. Yes, sir. Then we can take the coefficients to be common and we get the elements as this.
Okay.
Right.
Yes, correct.
So what is the subspace Vn here?
Yes. Yeah, just
Vn,
okay, just
Vn
wait.
one.
Let me explain. Okay, let me explain. Some network issue again and again. Okay. So yes, you know that 1x x square up to x n minus 1 is a basis. Okay. For this without any condition. So what condition is given? The coefficient of each term, sum of the coefficient of each polynomial in this are 0. So if we make this one as the coefficient of each polynomial becomes 0, just a visualization, it's not complete solution, just after getting solution you can approach by this, you can think like this: 1 minus 1 x minus 1 x square minus 1 up to x minus 1 minus 1. So this will become 0, you can remove this one because this will make this linearly dependent set if 0 will be there. So if you remove this one, then you will get this one is linearly independent, and the condition that the sum of coefficient plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, the coefficient becomes 0. Now to prove, now we take any, okay, let me write this one is little bit more. Okay, now you take any polynomial in this is the form alpha 1x plus alpha n minus 1 x power n, and this condition is given, so we can write this one as alpha naught, this the same thing that he told. You can write this as minus alpha 1 plus up to minus alpha n minus 1. So just write alpha 0 minus, sorry, alpha 1, not alpha 0. We are writing minus alpha 1 minus alpha 2 minus alpha 3 minus alpha n minus 1. This is we have written at the place of alpha naught, and all other terms are alpha 1x up to alpha n minus 1 x to the power n minus 1. Is it correct up to here? After that you can write this one alpha 1 x minus 1 plus alpha 2 x square minus 1, and this one is alpha n minus 1 x power n minus 1. So you had chosen any arbitrary polynomial in this, which is this one, and we are writing it as a linear combination of this term, and this term, because alpha 1, 2 and n minus 1 are scalar. So we can say that any polynomial in this set W, we can write it as the linear combination of x minus 1, x square minus 1 and x minus 1. So this will become form basis. Basis means it become especially spanning set, not exactly basis. So we can say that this set V equals to x minus 1, x square minus 1 up to x power n minus 1. This is an spanning set. Now we have to show that this is a linearly independent set also. Then we say this B form basis for this W. So we get the spanning set, and then we prove, and this part is easy, not tough. Just compare the coefficient after writing alpha 1, x minus 1, alpha 2, and you will get it. So okay, have you got it, this question? Initially I was trying to reduce alpha n minus 1, that there was the problem. I have to reduce alpha 0, then we get this form. It is clear, everyone? Any comment on this question or any other approach?
Yes, sir, it is clear.
Okay, any other approach for this one? Sumin Mandal or anyone? Anuj?
No, my approach was same like he said.
Yeah. Okay. So this one is good approach. Initially, I was trying to reduce alpha n minus 1, but you have to reduce alpha 0, then you will get this solution. Okay, so time is over. So if anyone has any doubt or any special question asked, so he or she can ask, because I think this one is last class before minor. So anyone has any doubt from anywhere, so please ask. And everyone has know how to upload answer sheet on Gradescope and all that thing. And paper will be uploaded on MS Team and Gradescope both places. So you can find that paper. Okay, let me show once where you can find this paper actually. Okay, just wait. My screen is visual now. So when you go in MS Team, okay, in linear algebra course, here it is files option. So in files, here it is class material. So here I will upload the paper in this form. Okay. So everyone paper, you will find paper here and on Gradescope both places. So yes, if anyone has any doubt or any problem, please ask. Otherwise, we can wind up here. Okay, so no question. Thank you all. Now you can leave the meeting.